Okay, so in this lecture, we are going to start a discussion on different types of transducers and their operating principles. And to start, what is a transducer? I have already mentioned in the previous classes that it is a device which is used to convert energy from one form to another. Now, the process of converting the energy from one form to another is called transduction, and the device that performs this task is known as a transducer. And in most of the cases, the signals or the quantities that we want to measure are in non-electrical form, the physical quantities that we want to measure. So in order to incorporate electrical methods of measurement, they have to convert it into electrical energy or electrical form. So I mean, in this course, we are going to later on discuss the operation of different types of electrical transducers. And what are the advantages of converting the physical quantities into analogous electrical quantities? So once the physical quantities are converted into electrical form, then the electrical process of amplification or attenuation can be done with static devices. Now, compared to mechanical devices, you know that mechanical devices consist of rotational parts, or there are different gear mechanisms. So those actually cause so the mass inertia or the friction effects are significant over there. So after using those devices, mechanical devices, for a long time, there is wear and tear in those devices and they become inefficient after using for a long time. Now, compared to that, electrical devices are static devices, and uh, I mean, they are free from this mass inertia or friction effects that the mechanical devices suffer from. Now, the electrical transducers or the whole electrical system can be actually controlled by a very small power level, or small voltage supply or current supply might be sufficient for controlling the electrical transducers. And also the output form, the output when it is generated in electrical form, it can be easily manipulated. I mean, if it is necessary to amplify or filter out some portion or any sort of signal conditioning, or if the signal has to be transferred to a distant place, that can be done once it is converted into electrical form. Now it can be converted from analog to digital form, then or even in form of electromagnetic waves, it can be transferred in two different locations. And also the storage is easier after converting it into electrical form. I mean, from analog to digital conversion, then the digitized data can be stored in computers, or they can be displayed using 7-segment display or LCD or LED displays. So these are some of the advantages of electrical converting a signal into electrical form using electrical transducers. And it has been mentioned already that for transferring data into a remote location, and uh, it is not possible to transfer a mechanical data from one place to another. However, once it is converted into electric form, it can be transferred, and in the receiving side, it can be decoded, and the useful information can be restored in the receiving side. And also with the development of the electronic ICs and the different transistors, the measuring equipments have become it has been possible to miniaturize the sizes of different measuring instruments. So that is also another advantage of converting a signal into electrical form using electrical transducers. Now, if we talk about the classification of transducers, in several ways the classification can be done. So the first one that is shown over here, that is with respect to the electrical circuit parameter that is intended to be changed with respect to the change in the physical quantity. So the change in a physical quantity that is going to be transferred into an equivalent change in some electrical circuit parameter. So which parameter is varied, or which electrical circuit parameter is varied, with respect to that a classification can be done. So in that sense, the classification can be said to be the transducers can be said to be either be resistive type, or capacitive type, or inductive, or even directly voltage and current. And also there are other optoelectronic transducers also available there, which convert the photon energy into electrical energy. So in this way, this classification can be done depending on which form of energy we are converting the signal to. Now, with respect to the functionality of the transducers, now they can be classified as primary transducer or secondary transducer. Now, if we recall the fundamental block diagram of any measurement system, which was discussed at the very first class, so we had two blocks in the initial stage that were the primary sensing element, and which was followed by another block, transducer. Now, it often happens that both these functions are done by a single transducer. So a separate primary sensing element is not necessary. In those cases where a separate primary sensing element is not necessary, the physical parameter can be sensed and it can be directly converted into a desired electrical form. In that case, the transducer is said to be a primary transducer. For example, thermocouple. So thermocouple doesn't require an intermediate sensing element. The physical change in the temperature, it can directly convert to the change in EMF. So we can say that it is a primary transducer. Whereas in secondary transducer, it is necessary to detect the change in the physical quantity using some primary sensing element. Then the detected output is further processed by the transducer to convert it into electrical form. So these transducers, which require the help of another sensing element, these transducers are called the secondary transducers. And for example, here, for a particular pressure measurement equipment, often a mechanical transducer or mechanical tube called the Burden tube is used to detect the pressure first, and it detects the pressure and converts it into analogous displacement. So the displacement is later on converted into a desired electrical form. So the energy conversion over here that takes place, so from pressure, first the mechanical transducer converts it to displacement or motion. Then it is converted into an electrical form, suppose change in resistance, by the secondary transducer. So for example, if we consider a linear potentiometer or linear variable resistor, so we know that the uh, linear variable resistor we can say that it has three terminals, A, B, and C. So A and B are the two fixed terminals, and C is the movable terminal, or you can say that it is the slider of the potentiometer. So if the slider is attached with the displacement that is being uh, generated by the mechanical sensor, then with respect to that displacement, this slider will move back and forth, and wherever, at which location the slider is located, with respect to that, the corresponding resistance can be considered to be the equivalent change in the displacement. And as displacement is resulted through pressure, so that equivalent change in resistance can be actually related to the original change in pressure. So the change in pressure will result in displacement, and the change in displacement will result in change in resistance. So in this way, the secondary transducer can relate the change in pressure with change in resistance. Now, another classification can be done with respect to the requirement of external power supply. So if the transducers do not require any external power supply or power source, then they are termed as active transducers. So rather they actually generate current or voltage directly in response to a change in physical quantity. So again, we can bring the example of the thermocouple. So there is no external power required. Rather, when there is temperature difference, the thermocouples can generate EMFs. So in this way, they can be termed as active transducers. And piezoelectric transducers. So these transducers are designed with piezoelectric materials. So piezoelectric materials are materials which generate electricity when there is some deformation in their shape. So if there is some mechanical stress or force applied to piezoelectric materials, so their shape are deformed, so the crystal structure are deformed, and that results in generation of some electricity. So those can be also classified as active transducers. And from optical transducer, we can say that photo cells or photo detectors can be termed as active transducers, or you can also say solar cells, because they directly convert the sunlight into electrical energy. So it can be said that they are also active transducers. So in this way, actually several examples can be found of active transducers. Now the passive transducers are the transducers which require actually external power supply. So most of the resistive, inductive, or capacitive transducers are passive transducers. So they require energy in one form or electrical energy in one form or another to extract meaningful results from those transducers. For example, a strain gauge, this is a resistive transducer, then RTDs, resistance temperature detectors, thermistors. So all these resistive transducers actually require external power supply, thus they are passive transducers. Now let us elaborate our discussion with resistive transducers. Now, resistive transducers are the transducers which convert any change in physical quantity into change in resistance. So what could result in the overall change in the resistance of a particular material? So you know the general expression which is used to represent the resistor of a particular material. So it is dependent on the resistivity of the material, the length of the material, and the cross-sectional area of the material. So if any one of these or multiple of these three variables can be varied with respect to the change in the quantity that you want to measure, then actually uh, the physical change can be represented in terms of the change in resistance. So in most of the cases, uh, for temperature measurements, resistive transducers are used because the resistivity of the material is dependent on the temperature. So if there is temperature difference, then the resistivity will change, which will cause change in the value of the resistor. So in most of the cases for temperature measurement, resistive transducers are used, and also for strain, displacement, force, or pressure. These different resistive transducers are often used because for any force, strain, or stress, apart from or along with the resistivity, the length and the cross-sectional area will also change. So for these changes, the resistive transducer can be incorporated to measure the force, pressure, displacement also. Now, if we move on, now linear potentiometers and rotary potentiometers. Okay, actually these things are known to you, nothing new to discuss over here. Now the construction of the linear potentiometers, I believe it is also known to you. So there is resistive element present inside and the chamber, and there suppose this is terminal A, this is terminal B, and in between them there is the slider which is having a mechanical contact, metallic contact associated with the resistive element. So wherever the position of the wiper is, with respect to that, suppose if this is terminal C, the resistance between terminal A and C can be determined. Okay, for example, if the linear potentiometers, if you want to use these potentiometers to measure uh, linear displacement, suppose this is terminal A, B, and this terminal C is representing the slider. Now, the whole resistance between terminal A and B, suppose this is RAB, and let's say using this total resistance of RAB, a linear displacement of L, maximum displacement of L uh, uh, could be measured. Suppose L is equals to 1 meters. So up to 1 meter displacement you want to measure using this linear potentiometer. So we can say that the value of the resistance RAB corresponds to 1 meter. So if there is any displacement which is coupled with this slider, so with respect to that displacement where the slider is located, the resistance of RAC up to that point can be determined. So what fraction of RAC to the total resistance, that you can determine and multiply it with the total length, and you can approximate that what was the approximate displacement in the physical quantity. So this standard or limit of the length that you want to correspond with the total resistance, depending on that the change in displacement can be used to determine the change in resistance and predict the linear displacement. Now, rotary potentiometers. Now, you also are quite familiar with rotary potentiometers. You have often used this in your different labs. Now, you know that there are 3 terminals. Among the 3 terminals, 2 terminals are fixed, and there is the other terminal, which is the variable terminal or variable end, which is coupled with the variable knob. Now, the rotary potentiometers, they can be often used to measure rotational displacement. Now, suppose for the figure shown over here, this total length, this semicircular arc shown over here of resistive material or resistive track, we can say that it is corresponding to a 180 degree. So depending on the position of the wiper, suppose we want to determine this angular shift or theta. So how we can do that? We know that because it is a semicircle, it is 180 degree. Now the resistance between terminal 1 and 1 and 3, it can be easily determined. Then depending on the position of the wiper, the resistance between terminal 1 and 2 can also be determined, and there is our unknown angle theta and the total angle 180 degree. So if these 2 parameters are known, easily the unknown angular displacement can also be predicted by multiplying this fraction with 180 degrees. So these are simple examples of how linear and rotational displacement can be measured using resistive elements. Now this rotary potentiometer, for rotary encoders, often this mechanism is used. There are resistive rotational encoders that you can use along with different microcontrollers to predict uh, predict angular displacement. However, their accuracy is low, whereas optical encoders provide better accuracy. But due to the simplicity of the construction, they could be simple solutions for predicting angular displacements. So we have been discussing on resistive transducers. So at this stage, we are going to discuss about uh, strain gauge, which is also a resistive transducer. Now, the working principle of strain gauge is dependent on the application of stress or strain in any form, which will deform the shape of a particular conductor or elastic material. So for this case, uh, in this cylindrical shape with the solid lines, we can say that this is representing a metallic conductor or metallic wire. So in this wire, if some force is applied or stress is applied in the longitudinal direction as indicated over here, so what will happen, its length will increase. So as the length is before the applying the stress, if the length is L, and after applying the stress, its length is increasing by delta L. So as the length is increasing after applying the stress, we can say that the longitudinal strain is then positive as it is increasing the length. Whereas due to the application of the force in this direction, the diameter of the wire will tend to decrease. So the lateral strain can be considered to be negative because the diameter is decreasing. And if d is the initial diameter, then after the stress is applied, the diameter can be represented as d minus delta d, where delta d is the change in the diameter. So as the diameter is changing, so obviously the cross-sectional area of this wire will also change. So as the length is changing and also the cross-sectional area is changing, so we can easily suggest that the resistance of this particular wire will also change depending on this relation. And apart from the dimensional changes, the changes in the length and the diameter, the resistivity of the wire will also change due to the applied stress. So the change in resistivity due to any applied stress or strain, this property of the material that due to applied stress, its resistivity is changing. It is called piezoresistive effect. So by that we can conclude that, I mean, due to applied stress, all the three variables upon which the resistance of a material is dependent are varying with respect to the application of stress. So for the time being, let us consider that uh, uh, when the wire was unstrained, when there was no strain applied, then the resistance of the wire can be represented as R equals rho L by A. Now after the stress is applied accordingly as indicated in the figure, suppose a small stress S is applied, which is going to cause a positive longitudinal strain and the negative lateral strain. So the change in length is delta L. So the change in diameter is delta D, which will cause a change in the area also. And the overall change in the resistance can be represented by delta R. So we are going to use these symbols in later derivations. So we are going to go for deriving the gauge factor. So that is actually going to give a measure of the sensitivity of a particular strain gauge. So in order to do that, first of all, the expression, which was the simple expression R equals rho L by A, that was also written in the previous slide, we are going to differentiate that with respect to the applied stress S. Now remember that all the three variables rho, L, and A are function of the stress S. So we are going to have to take partial derivative of all these three variables with respect to S on our right hand side. So that is being actually done over here. So I think that it is quite straightforward, and with one or two lines you can easily do that. So after taking the derivative on both sides with respect to the applied stress S, we can get this relation. Now on both sides we can divide by the resistance R, and once we do so, we will end up with this form of the initial expression. So obviously uh, I'm saying that we are dividing both sides by R, but on the right hand side we are actually not considering R itself, but we are considering rho L by A. So if you divide the right hand side with rho L by A, you will see that you are actually getting uh, you are actually modifying the previous line with this one. Okay, so up to this point you'll see that the relation is represented in terms of the change in length with respect to the change in stress or applied stress, then change in cross-sectional area, and the change in resistivity. However, the area is getting changed because of the change in diameter. So this equation is further going to be modified with respect to the change in diameter, because as shown in the next slide, the area can be easily represented in terms of the diameter. And here also, if on both the sides partial derivative is taken with respect to the applied stress S, then a relationship between the area and the diameter can be formed in this way. So once this relationship has been established, so this term on the previous equation this term can be actually replaced with the modified term. So after replacing 1 by A into del A by del S with this in terms of the diameter, the modified expression will be this one. And in order to further simplify, a constant is going to be introduced over here, that is called the Poisson's ratio. So the Poisson's ratio, because we are not going to actually keep both while we are going to further simplify, we are not going to keep both the length and the diameter. We're going to try to reduce it into less number of variables. So using the Poisson's ratio, what we are going to try to do, we are going to represent the change in the diameter with respect to the change in length as well, so that we have to deal with only one variable. And we are keeping the length over here because as the longitudinal strain is considered to be positive, so that's why for this particular case the whole thing is going to be transferred into corresponding uh, change in lengths. So the Poisson's ratio is defined as the ratio between the lateral strain and longitudinal strain. So you can easily say that it is actually a dimensionless quantity, because similar units are there on both the numerator and the denominator. So the lateral strain, which is causing the change in the diameter, so that can be termed as delta D by D. So delta D is the change in the diameter, and D can represent the initial diameter. And as this change is negative, we have to put this negative sign, and the longitudinal strain as the length. It can be defined as the ratio between the change in length to the initial length. So in this way, in terms of the Poisson's ratio, we can have a relation between the change in the diameter and the change in length, and thus this term over here we are going to replace it with this term over here. And the Poisson's ratio for different materials, it is different, and it is a known quantity. So if the chart of the Poisson's ratio of different materials is available, then easily that value can be put in the equation, and the necessary calculations can be done. Okay, so now in this equation, the del D by D term is getting replaced with this one, and after doing that we'll end up with this expression. So let us go to the next slide. So in the next slide, the same equation is actually written in a different way actually. So just different symbols are used. So in terms of small variations, the same previous equation can be represented as this one. So here the dr by ds is representing the change in the quantity. Similarly, the del L by del S is representing the change in the length, and del rho by del S is representing the change in resistivity. So all these terms are actually replaced with delta R, delta L, and delta rho. So just indicating the change in the corresponding quantities due to the stress, and the corresponding equation is written in this format. Now let us define what is the gauge factor. So gauge factor is the fractional change in the resistance due to the change in applied strain. So let us consider, or we initially considered that the stress is being applied in the longitudinal direction and it is increasing the length. So in terms of the length, we can represent the fractional change in, so the fractional change in the length can be actually representative of the applied strain or applied stress. So the ratio of the fractional change in resistance resulted due to the fractional change in length is actually defined as the gauge factor. So this is also a measure of the sensitivity of the transducer, because for the same amount of stress applied, if different materials show different fractional change in resistance, then the material which is showing higher more uh, change in the resistance, or whose gauge factor is higher, that can be termed to be more sensitive to small amount of applied stress, and that can be used for sensitive detection. So the gauge factor, now in terms of the gauge factor, we are going to convert this equation in terms of the gauge factor. So for that, we are going to divide both the sides by delta L by L, and if we do so, what we are going to have as our expression for the gauge factor is 1 plus 2 into V plus the ratio between the fractional change in resistivity to the fractional change in length, or the ratio between the fractional change in resistivity to the applied stress. So this is actually the generalized expression for the gauge factor. Now, in this gauge factor, expression of gauge factor, the three terms are actually signifying or uh, indicating the or resulted from the change in three different quantities. So this first term is actually resulted from the change in r due to the change in the length. If you remember the first expression that was written, then the second term is due to the change in the area, although we later on represented it in terms of first in terms of the diameter, then in terms of uh, the length. But however, the initially that this term is actually resulting from the change in area, and the last term is resulting from the change in resistivity. So the property of the variation in resistivity due to applied stress, it was defined as the piezoresistive effect. So these three corresponding terms are referring to the variation in the three different quantities: length, area, and resistivity. Now, for a particular material, if the piezoresistive effect is negligible, then the gauge factor can be represented in terms of this expression, which is 1 plus 2 into Poisson's ratio. So for a particular material, if the Poisson's ratio is known, then the gauge factor can be easily determined, and from the gauge factor, the sensitivity of the corresponding strain gauge can be also approximated. Now, for all metals, the Poisson's ratio is normally between 0 to 0.5, and the common value which is used for the Poisson's ratio for different types of wire is 0.03. So if you are doing any maths or doing any calculations, if the Poisson's ratio of the material is not used, then you not defined, then you can use this standard value of 0.3 as the Poisson's ratio and calculate the gauge factor. And if it is defined, then you can easily use the value from the calculate the value from the given data. And the unit for the strain for this sort of strain gauges, the strain which is applied unit is defined as microstrain, and 1 microstrain is actually equivalent to 1 micrometer plus 1 micrometer per change in per meter length. So like we defined the strain to be delta L by L in the longitudinal direction. So for 1 meter length of a wire, the change change in the length is 1 micrometers. So that is actually, in that respect, actually the unit of the strain is indicated in terms of this sort of calculations. Now while you are using strain gauges, it would be required for you to measure the resistance of the strain gauge. So that resistance can be done, measurement of the resistance can be done using Wheatstone bridge. Now, why the measuring the resistance of the strain gauge is necessary? Because suppose there is no stress applied, you have to know the value of the strain gauge when it is unstrained. So suppose oh, you are connecting the strain gauge in a Wheatstone bridge circuit in one of the arms, and when it is not strained, in that condition you are balancing the bridge. Now the bridge is in the balanced condition, and if you connect a voltmeter between these two nodes, it is supposed to indicate 0. However, if the strain gauge is experiencing some strain or force, its shape will be deformed, and that will cause a change in its resistance. So whenever there is change in the resistance due to the unbalance caused by the change in resistance, the voltmeter is no longer going to give you 0. So there will be some changes in the values or some reading shown in the voltmeter depending on the potential difference between these two nodes. So from the change in resistance, there is a resultant change in voltage. So with respect to the change in voltage, the uh, the amount of applied stress or force can be predicted. So for some known amount of pressure or force, if the corresponding changes in voltages are measured, then a scale can be calibrated. So whenever any unknown force or stress is applied, then with respect to that scale, the unknown force or strain or pressure can be predicted. Now regarding the construction of the strain gauge, you can see a particular construction is shown over here. So this type of construction is called the bonded wire strain gauge. So in this sort of construction, there are normally 3 layers. So the upper layer is called the felt, and there in the bottom layer there is a flexible piece of paper on top of which the mm, conductive material or the metal which is used for the purpose of constructing a strain gauge, that is placed over here. And from the top view we can say that the conductive material is actually placed in a zigzag form. That is actually done to incorporate a I mean incorporate a larger length of the material within a smaller space, because I mean it is not possible that you are going to place a long string, so the size of this transducer is going to become uh, large. So rather, in order to uh, compact the size of the strain gauge, so the wire is actually placed in a zigzag form, so that within a very small area large amount of the wire can be placed easily. So uh, this is a general simple construction of a strain gauge. So moving on to to this chart. So this is a chart where for different types of materials, the corresponding gauge factors are indicated over here. So these are some common I mean materials which are often used to I mean to construct the strain gauge. And lastly, for some applications, so for structural stress analysis, strain gauge can be used. So for example, uh, for smart bridges, in order to keep the bridges in good condition, or whether they're overstressed or not, to monitor those, strain gauges can be used at the bottom or placed at the bottom of the bridges, so that if there is too much stress on the bridge, so that there those I mean uh, those incidents can be monitored properly. So there could be hundreds of such sensors placed at different locations underneath the bridge to observe the overall stress experienced by the bridge when there is different vehicles traveling on top of it. So And also, it has been already mentioned that for measurement of force, pressure, or flow, the strain gauge can also be used. So for example, two figures are shown over here. Suppose this is the test material, and on top of which a strain gauge is attached, and we are also connecting this strain gauge to one of the arms of the Wheatstone bridge. So whenever suppose a force is applied in the downwards direction, like it is shown over here, so what is happening, the strain gauge is going to get expanded. So if it is getting expanded, the uh, overall length of the conducting material which is placed on the strain gauge, the length of the material will increase, and as the length of the material is going to be increased, that will cause the resistance to increase as well. And in the previous case, when the bridge was balanced, when there was no force, now as the resistance is going to be increasing, this will cause an imbalance to the bridge, and there will be some change in voltage along this along which can be read through the voltmeter. So in this way, again, if the force is applied from the other direction, then what will happen, the strain gauge is going to be compressed, uh, and if it is getting compressed, this resistance is going to be decreased. Then whatever the voltage reading was obtained previously, now the reading will be reversed, or the polarity of the voltage will be reversed. So uh, from that, it can be suggested uh, that whether the force is applied in upward directions or downward directions, and from the magnitude of the voltage, it can be detected with how approximately how much pressure or force has been applied. So in this way, different types of analysis can be done. So this is a very general discussion on strain gauge. Now there are other types of resistive transducers as well, which are used to measure the variation in temperatures. So in the next lecture, we are going to start our discussion with uh, different resistive sensors which are used to measure temperature differences.